All right. Should we go back to the lectures again? Does someone want to hear the explanation? Because some of the students figured it out in the break what was going on. Does someone want to hear the explanation for the experiment? Yes? Okay. So I draw the figure again, I guess. I have a laser here. I have this prism, and I have total internal reflection right now, right? Because K parallel is less than, well, shoot me if I'm wrong, but let's say epsilon r mu r omega square over c square. And epsilon r is about 2 or so in the prism. And mu r is 1 everywhere, because the glass is not magnetic, at least not enough to make any difference. So what's going on here? Well, now we had evanescent waves, right? So if x3 is here, then we have e to I k parallel r parallel. That's the part of the wave traveling along here. And there's an e to minus beta x3, where beta is now a positive number, so that we have an exponential decay. Or maybe yeah, looks right. So what we have here is some sort of wave going here, and then there's an exponential decay outside. But remember, what? Sorry. There you go. It should be bigger than this, of course. And then there's no, in the air medium, there's no geometric interpretation of theta again. We're in the evanescent case, and we have an exponential decay here. But of course, the field, I mean, even if the intensity transport out here somewhere at some detector is 0, it doesn't mean that the electric field just at the interface is 0, because the electric field must satisfy the boundary conditions at all times, everywhere, or everywhere on the interface. This means that there's some non-zero electric field here. And if I now cleverly insert my lens here, or some other object which just gets close enough, you can also do it by putting flat objects together and squeezing. But that's a bit more troublesome. Okay, so I put the lens here. Well then, because, well, if I look at the expression for K parallel, let's see. I have that K parallel, or alpha. No, sorry. Yeah, I look at alpha is equal to omega square minus K parallel square. I skip the constants for now. Well, no, I don't actually. I would say epsilon mu. Okay. And now, in this case, where I had the air, I had the epsilon mu is equal to 1, or epsilon 0 mu 0. And then I have to change the order, and I get out an I. And this causes the evanescent decay. But when I get back into the glass again, epsilon and mu is back to roughly the same value as the glass. It doesn't have to be the same, but it just has to be enough that we can again flip the sign inside the square root and get away the I. Because the thing causing the problem here was that alpha went to I beta when we came from glass into air, right? We had a positive, or at least real number inside the glass, and it turned into a pure imaginary number, causing the exponential decay. But when I get back into the glass again, the epsilon and mu get big enough that I can flip the sign, I get rid of the I beta, or the I, and we're back in business. So the wave starts propagating again. And of course, this means that less energy comes out here. Otherwise, energy is not conserved. So because the electric field is not 0, even if the intensity is 0, then we can just pick it up and then increase the intensity again. And if you want to see why this is the case, you can calculate the Poynting's vector. Calculate that for a plane wave in glass. We went through the formula last time. And then calculate the S for the evanescent wave. And you'll see that there's no energy transport here. So you have to put some medium to pick up again the electric field. So total internal reflection is not always totally internal. And this is in fact used in some measurements of really small structures, because K parallel was larger than this, meaning you essentially get a shorter wavelength than the vacuum light. So actually some multi-touch panels use this principle. You have some sort of glass pane here where you have light, and then if you put your finger on it, well, then you have some scattering of light because it changes the boundary conditions. It's not just air everywhere, it's something here. And then you get scattered light from that point, and then you have detectors on the backside of the display. I don't think this is how most mobile phones work, but there's some touch displays that use this technology. It's called frustrated total internal reflection. It's not a joke, it's true. And I'll put a YouTube video on the homepage so you can have a look again at where someone did a really nice video of the phenomenon, also for those who are not here. Yeah, frustrated total internal reflection. Any more questions about frustrated total internal reflection? Nothing? Okay. Yeah. Okay, we went through the dispersion relation curve. Oops, I'm running out of chalk. We went through the dispersion relation curve for the case of air over some sort of, let's say, glass. But now what happens if we have several layers? I put a metal substrate here. Then I put a thin film of glass. It could be more or less anything, but let's call it glass for now. Then I have air on the top of that. So when I shine light here, what does the dispersion relation look like in the air and in the glass? And by the way, in the metal, we're evanescent for all K parallel because there's conductivity losses in the metal, meaning that there's always something that gives you an exponential decay. So you can have an oscillating wave which decays quite fast. So let's see, evanescent for all K parallel inside the metal. Now I can plot the dispersion relation as follows. Let's see, I have my source frequency and K parallel. Now the light line looks different from air and the glass because epsilon and mu is larger in the glass. This is the source frequency. And we now have three regions in the K parallel omega plane. And that's to the right of the glass light line, between the air and the glass light line, and to the left of both light lines. And now let's see what's going to happen. In region 1, then we're to the left of both light lines, so we have propagating modes in both air and glass. So you get ordinary reflections bouncing back and forth. And the second case is that we have propagating modes in the glass because we're to the left of the glass light line, but we're to the right of the air light line. So we have evanescent in air and propagating in glass. So propagating in glass and we have evanescent waves in the air, meaning that if we, let's say, we shine some light in here, then it's going to be totally internally reflected in, and hopefully not too frustrated. So it's going to keep bouncing inside the glass without getting out into the air because you get an exponential decay in this direction. It's evanescent. And in the region 3, then we're evanescent in both air and glass because we're to the right of both light lines. And by the way, if you're interested in evanescent waves, there's a really nice problem in the book which gives you hints and goes through step by step the calculation for how an evanescent wave looks like, and you get to see what's going on in detail. It's really a helpful exercise. I don't remember the number, but I think you can find it in chapter 9. Okay, yeah, and in the metal we're evanescent for all wavelengths because we have conductivity. And this is one of the reasons why metals are nice mirrors. Okay, but now we took a large detour into dispersion relations, so let's get back to the scattering problem, which is if I have incident light, how much is coming out and how much is transmitted. Any questions to this figure? Okay. Okay, now let's draw the figure again. Let's see, we have the interface, surface normal, incident, reflected, x3, x1, and I call the wave vectors k, q, and p. And for now I'm going to assume that the incoming wave k can be scattered into any wave q and transmitted into any wave p, and then we'll see how far that takes us. But first of all, let's establish the boundary conditions, because as we just saw here in the experiment, the boundary conditions are important. They tell us how the electric field behaves at interfaces. And there are two boundaries, so to speak. First one is at x3 is equal to 0. And that's this interface right here. So I have, let's see, medium 1, medium 2. So the interface between those two media. Then from the Gauss law, I have that E1 parallel is equal to E2 parallel. No, that was from Faraday's maybe. Okay, anyway. It follows from the Maxwell equations at least. H1 parallel is equal to H2 parallel. And the vertical components, let's see, that's 3, 4. I assume that there's no sources or no, that is, there's no source term. By that I mean there's no current, there's no charge at the interface. So we have also B1, B2 perpendicular. Okay. You've seen this before, so I won't discuss that anymore. But these have to be fulfilled by any solution we might find. And there's a different boundary which is less obvious perhaps, and that is at plus minus infinity. Now, what are the boundary conditions there? Well, if I send light in here, bounces up here, there's only going to be the incoming light and the outgoing reflected light at infinity. while down here there's only the light going downwards. So I can't have a, if I send in light here, I can't have a wave propagating upwards in medium 2. Everyone agrees, right? There's no source from that for that wave. So, well, if I had something down here, it could happen, but there's not at the moment. So there should be no return wave. Okay? So let's see. 5, we only have upward scattered wave in medium 1. The 6 is that we only have downward going waves in medium 2. Okay, that should be pretty intuitive, I hope. And now we're going to consider one polarization at a time. Last time we introduced the S and the P polarized waves, and just to recap, S is German for senkrecht, meaning orthogonal to the plane of incidence. The plane of incidence is the, let's see, plane of incidence is equal to the n hat k plane. That is, this vector and this vector form a plane. And S polarization is when E is orthogonal. So I'm considering an E field that is out of or into the board. It's going to fluctuate, right, because of the wave nature of the field. And we only work now with E2. Right? There's only a component going into or out of the plane for the E field. So E1 and E3 are both equal to 0. Yeah. So there we go. So to draw the fields perhaps more clearly. If I have a k vector like this, then the E field is pointing, let's say, into the board. And then it was k cross E, wasn't it? K cross E, so H is going down. Okay. In the transmitted medium, we have P vector. The E vector is still out of the board. And the H vector is orthogonal to the other two, so it's given. And for the reflected, same thing, okay? Like this. So now it should be clear what S polarization means. And P polarization is just the opposite, that the E vector is in the plane. P means parallel, right? And the H is perpendicular. Now, let's see. And we assume that the frequency of the incident light and the scattered light and the transmitted light are the same, so omega is conserved. And then we can drop the time dependence because it's going to be the same everywhere. Let's see. Yeah. And if I now need the H field, I can calculate this explicitly from Faraday's law. So I can solve only for E2 and then just calculate the magnetic field from that directly. And we do that as follows. We insert into the Faraday law. We assume a harmonic time dependence E2 minus I omega t, meaning that when we take a time derivative of the H field, I'm going to get down I omega essentially. The minuses are going to cancel, so I get I mu omega h from the harmonic time dependence. And now what is this E? Since there's only one component to this, it should be quite easy to calculate the curl of it. And let's see what the first component of the curl is. Epsilon 1 j k dj ek. That's the first component of this vector, right? So that's going to be the first component of this vector with some constants. Let's see. That is 1, 2, 3. That's a positive. So it's d2 e3. And then if I swap 3 and 2, I have to swap the sign. So it's d3 e2. And we know that this term is 0 because we said that we're investigating only S polarization. So I can skip this term, meaning that this is the only thing I get out for the first component of H. Okay, so we set the left-hand side first component equal to the first component of the right-hand side. And we get that H1 is equal to I over mu r u naught omega d3 e2. And we also get equivalently that epsilon 3 j k dj ek. That's the third component of H, or the third component of this curl, but it's going to give us an H. That is, of course, d1. Let's see, 3, 1, 2. That's positive, so it's d1 e2 minus d2 e1. This is 0 because e1 is 0, giving us d1 e2. And we have that H3 is minus I u r mu naught omega d1 e2. So this gives us essentially some component of the k vector. Okay, let's see. So when I determine E, yeah, there's a minus where? Here?
Minus E2.
There should be something here, you mean?
No, further down.
Here?
Yeah.
Is there a sign error? 1, 2, 1, 2, 3 is plus. 1, 3, 2 is minus. Am I in the wrong place?
Shouldn't that sign be a
Yes, but there's one on the right-hand side. Okay, there might be a sign error. I think you're right. Yeah. So probably there's a minus here, and then I guess there's a plus here, because I follow the same procedure. But okay, any blackboard signs I don't trust anyway. So yeah, but I think you're right. Anything else? No. Okay. Whew. So, I think I'll just wipe this out, if we all agree now. Okay, so we agree that I can just determine E2, and that will give me the magnetic field if I need it. So, total electric field in medium 1 that would satisfy the wave equation is the following. And now this is just, let's see, I'll write it like this, E1, 2. So it's the second component of the field in medium 1. It is equal to it's equal to E to I K parallel R parallel minus I alpha 1 x3. This is now the incident wave, right? K parallel and alpha, let's see, 1. So it's a downgoing wave, that's correct. And Rs, then the scattering amplitude from K parallel into Q parallel. For now I'm assuming that the two are different. You all know the answer that they're the same, but for now let's be general. And then there's the exponential. And now there's a plus here because this wave is going up. Alpha, okay. X3. Wow. Okay, that pretty much fills up the blackboard. That's in medium 1. And yeah, the minus here means downgoing, the plus is upgoing here. And this is the reflection amplitude from K parallel into Q parallel. Okay, so we assume that we send a plane wave in, and there's a plane wave coming out. It could, in general, be pointing in a different direction. Okay. And in medium 2, I propose a different electric field, where I will only have a downgoing field, of course. E2, 2 is... By the way, the S is Senkrecht polarization, because there's going to be a different one for the parallel polarization, right? ds of P parallel, K parallel. This is the scattering it's not a scattering, but it's the transmission amplitude from K parallel into P parallel. So I send in wave in some direction, some wave number, and there's one coming out in a different direction. And then there's E to IP parallel R parallel minus I alpha. Again, the minus means it's downgoing, which corresponds, which is consistent with the boundary condition. Alpha 1. Alpha 2. Sorry. When the 2, of course, in the alpha there's an epsilon and a mu, and I put that into the alpha, saying that alpha 2 has the other epsilons and mu's. P parallel omega x3. Okay. Right, I hope that was clear. And now we get to the boundary conditions, meaning that, well, we had 6 boundary conditions, and we put 5 and 6 into here right away because of the minuses and pluses at correct places, I hope. Meaning we only have an incoming wave and an upward scattered wave in medium 1, and only a downward scattered wave in medium 2. So let's start off in the logical fashion, meaning we start off with boundary condition 1. That is E1 parallel is equal to E2 parallel. You'll notice that E2 is parallel to the interface because it's perpendicular to the plane of incidence, so it's in this plane. So this is really the only boundary condition for the electric field. And to satisfy this, we have to say that E1, 2 is equal to E2, 2 at x3 is equal to 0. right? And well, this means that this is equal to this thing. So I was hoping to put them into a nice equation, but I don't think there's room for that. So if you look at this, we can just take away the I omega t, of course. Let's see.
X3 to 0.
We set x3 to 0, which means we can take away this term, and this term, and this term, right? Because we're at the interface. Makes sense. And then we now need that, let's see, this reduces somewhat to the more compact boundary condition that e to I k parallel r parallel plus r q parallel k parallel e to I q parallel r parallel, I hope you get the point anyway, is equal to t p parallel k parallel e to I p parallel k parallel. Sorry about the small writing, but you get the point. You put them on each side of an equality sign, and this has to be valid for all. Sorry, r parallel. This has to be valid for all r parallel, right? Because the boundary condition has to be satisfied everywhere on the interface. And there's a problem in the book, number 915, which I'll leave for you to solve. And the result of that problem is that k parallel is equal to q parallel is equal to p parallel. So the lateral wave number is conserved. Okay, and it seems reasonable, right? Because for all r parallel, this has to be true, and this only depends on q and k. So it makes sense that p has to be equal to q and k for the phases to match up at all times, the complex phases. So the lateral wave vector is conserved, and this has some interesting implications already. And the interesting implications are as follows. If we look at, first of all, q parallel equals k parallel. And if you look at that, what this means in terms of the angle, because now we're in the propagating regime, right? So this means that epsilon 1 mu 1 omega sine theta naught. This is the epsilons of medium 1. Let's see, like this perhaps. Theta naught is the incoming angle, and then that's q parallel, k parallel. Sorry, q parallel is equal to the same epsilons, omega sine theta r, where r means reflected. Well, now if you stare at this, you see that this is the same as this, and the omega is omega. And we're left with the fact that the sine of theta naught is equal to sine of theta r. And since the thetas can only be between 0 and pi halves, this must mean that the angles are the same. So by assuming a quite general shape for the incoming and outgoing electric fields, and using the boundary conditions, we just figure out that, well, we just found the reflection law. Incoming angle is equal to reflected angle. So now you know why that is so. It's not just empirical or something
Should
that's.
there be, omega divided by c?
It depends if these are relative or not.
Okay, right.
I haven't used the same everywhere, but so I think I put the r's where they're relative.
Okay, right.
I try to at least. Okay, so in that case, this is 1 over the wave velocity square. 1 over wave velocity, in fact, since this is a square root. Okay. Right? And now we also have that k parallel is equal to p parallel. And this would imply that, let's see, epsilon 1 mu 1 omega sine theta naught is equal to epsilon 2, and it's the same all over, except now we have the transmitted angle. And now you see that, well, the signs can't be the same because the epsilons are not the same in general. Omega is the same. This means that, well, this is equal to the index of refraction n in region 1. Sorry, it should be Roman. So this is n1 times c, n2 c, where n is the index of refraction that you know from before. And now you'll see that the c's are also the same, of course, it's a constant. And we have n1 sine theta naught, n2 sine theta t. And this is what is called Snell's law. As you can see, it fell right out of the boundary conditions. In fact, only one of them. And yeah, I forgot what I was going to say, but this is Snell's law. So now you see that Snell's law follows directly from Maxwell's equations and some assumptions about the media. In fact, some people have created materials in later years where the index of refraction is such that the transmitted wave goes like this, meaning you need a negative index of refraction. So you can actually do this these days by structuring the material in a clever way. And then you're kind of stumped with Snell's law. But if you go back to electromagnetism, you can understand why this is so and what's going on. Okay, and since the k parallel is equal to p parallel is equal to q parallel, we also have that, let's see, we have an important equation, which is that 1 plus rs, because now the exponential phases in the boundary conditions are the same. Then we need to have that 1 plus rs is equal to ts, where these are the amplitudes of the reflected and transmitted electric field. Okay. And now we need another boundary condition, because we want to find out what is rs and ts, but we only have one equation and two unknowns. So I need one more equation, and then I'm going to look at another boundary condition. I'll call this equation 1. And there better be a number 2, or we're going to be stuck. Let's see. We also have that H1 parallel should be equal to H2 parallel. And let's see. Is that correct? Yeah. And the parallel component is H1. Let's say this is more correct. In domain 1 and domain 2, at x3 is equal to 0. These must be identical. And h1, the first component of the h field in medium 1, that is equal to I over mu r, mu naught, omega, d3, e2. We derived this in the previous lection, right? A few minutes ago. And let's see. So if I insert this for medium 1 and medium 2, it's the same in medium 2, except I have 2 in both places. Then I get out that the normal derivative, in fact, is continuous, right? Because this is a normal derivative. Okay, so I over mu 1 omega d3 e2 medium 1 x3 is equal to 0. Same thing in the other medium. Okay, now first of all we calculate the derivative, and we will simply get down an I alpha, right? D3 e to I k parallel r parallel. This is in the plane, but this is out of the plane, so it's not going to touch this. Plus minus I alpha. Plus minus because we have one wave going down, 2 waves going down and 1 going up, so I'm interested in both cases. K parallel omega x3. So this derivative is only going to get me what is in front of x3 because it's an exponential function. So I get down I alpha e to I, and you know what this says. Okay, and from that we have the following: minus alpha 1. The minus follows from the downgoing wave, the incident wave, over mu 1. Well, that is a plus because I now have an upgoing wave, the scattered one, Rs, times alpha 1 of k parallel omega mu 1. Left hand side of the equation, this side. And on the other side I'm going to get something similar except with a t in front, and it should be a minus sign because I have a downgoing wave here as well. So I get minus ts alpha 2. Oh, I should use Roman numerals. In medium 1, medium 2, right? And alpha 2 of k parallel omega over mu 2. Right. So now all of these depend on k parallel omega in the same way. No, sorry, that was harmful. There's no omega dependence here, of course. Just multiplication. Okay, so now this forms another equation. So if I just drop the k parallel and the omega, I get the following, which is alpha 1 over mu 1 Rs minus 1 equals minus Ts alpha 2 over mu 2. And this is a linear system of equations, 2 unknowns, 2 equations, and they're not linearly dependent. So next week we're going to see what happens when we solve them. Then we're going to find Rs, Ts, and we're going to know everything about the reflected and transmitted fields. Any questions? Okay, see you on Monday. And by the way, Friday 10:15 is the last chance to get any help on the midterm project, because that's the last exercise, and Saturday is the deadline. So remember that.